Wonderful, guys, let's continue in our adventure of the limit of functions. Now in this case we are going to be solving more example. Before we solve more example, let me quickly introduce to us a rule, a principle. Now we have what we call the L'Orbital rule. The L'Orbital rule is just simply taking the partial differentiation of functions, of individual functions in an equation or an expression. Now we only take the L'Orbital, or rather we only use the L'Orbital rule when we are dealing with functions that have no limit. So functions that at the surface we think has no limit, we can use the L'Orbital rule to get a limit for that function. Now let's look at some examples. Look at this first example. It says limit exponential 2x as our x tends to 0. As we know, what do? We put the value of this 0 into this formula. So if, in this case we have exponential 2x. So if we put 0 here, we have 2 times 0, right? And 2 times 0 is 0. Exponential 0, if you press your calculator, will give you 1. So in this case, we have a limit for the function exponential 2x as the variable x tends to 0, which is equals to 1. Now let's look at the second function. In this function we can see that we are looking for the limit of this function as our variable x tends to 3. Okay, putting it in our equation, instead of x I have 3, so I have 3 squared minus 9, then I have 3 minus 3. 3 squared is what? 3 squared will give us 3 times 3, which is 9, right? So I have 9 minus 9, I have 3 minus 3. 9 minus 9 will give us 0. 3 minus 3 will also give us 0, giving us a value of undefined, right? Now let's look at what this is saying. It says when we get a value of undefined, after trying to find the limit of a function, you can make that function have a limit. So undefined means the limit of the function is undefined. That means there is no value. Is that okay? Okay, now you can make that function have a limit by using L'Orbital rule. L'Orbital rule in essence, it means to take the partial differentiation of each function in that expression. Now example, I have x squared. Now the partial differentiation, now let's quickly touch differentiation before we actually go into differentiation as a topic. If I have a raised to the power of n, and this is my function, let's say y is equals to a raised to the power of n. To differentiate this function, I have dy, then I have dx, right? Okay, I have dy, then I have dx. Dy dx will be equals to this n will multiply a, so it will be n times a. So the power multiplies the base value, then you subtract 1 from the power. Is that okay? That's what happens when you differentiate a function. Now if I have another function like y is equals to a raised to the power of x, right? Now I can say y prime also is equals to dy dx. Is that okay? Y prime meaning we are taking the first differential of this function. So we use the raised to power, that's the index number. We use this index to multiply a. Is that also? So we have x times a. Then we subtract 1 from the raised to power, so we have x minus 1. I believe we all understand this. Let's do one more example before we go into our question so that we can get a better understanding. If I have y equals to 2x squared and we have to find the differential of this function in respect to x, so we say dy dx, or we can say y prime dy dx is equals to, now this 2 multiplies our base value, which is 2x, right? So we have 2 times 2x, right? Then we subtract 1 from the raised to power, so we have 2 minus 1. So this will give us 2 times 2 is what? Is 4, right? So we have 4x, 2 minus 1 is what? Is 1. So this is our differential value. Are we following? Wonderful. So now having x squared minus 9 over x minus 3, applying the L'Orbital rule means we are going to differentiate this partially. So we differentiate the expressions one by one, picking x squared. If I have, let's clean up our slide. If I have x squared, to differentiate this, what happens? 2, we get 2 times the coefficient here is 1, right? So we have 2 times 1x, then we have 2 minus 1. Is that also, which will give us what? 2x. 2 minus 1 is what? Is raised to the power of 1, which can also be 2x, and that is why I have 2x here. Now if I differentiate a constant, once you differentiate a constant, it will give you 0. So this is 2x minus 0, right? Now if I differentiate x, if I have x here and I differentiate x, what am I doing? How am I getting 1? Now what I get is that the 1 comes down to multiply x, right? Then I have 1, so I subtract 1 from the raised to power. So what I'll be having is 1 times x is what? Is x raised to the power of 1 minus 1 is what? Is 0. And anything raised to the power of 0 is what? Is 1, right? And that's why I have 1. If I differentiate 3, which is a constant, what will I get? I have minus 0. So 2x minus 0, 1 minus 0 will give me what? 2x divided by 1. And 2x divided by 1, as we know, will give us 2x. So differentiating this function partially gave us what? 2x. And what do? What we do is that since we now have 2x as our function, so x as it tends to 3, we just put it into this. So we have 2 times 3, which is equals to what? Equals to 6. And just like that, you see, we've gotten the limit of the function to be equals to 6. So therefore the limit of the function after using the L'Hopital rule is 6. So when you limit a function and you're getting a value of undefined, what do? You take a partial differentiation, or you use the L'Hopital rule to find the limit of the function. I hope you all understand. Wonderful. So I believe we are getting somewhere. So we are through with the limit of the function. What we are doing is solving examples. So in our next video, we are going to be solving more examples under the limit of a function. We're going to be looking at tougher examples before we finally go into differentiation as our topic. So thank you guys for watching. Thank you for listening. Make sure you like and comment, and make sure you subscribe to my channel below.